Good day, my name is Shinro. Today we are going to introduce deep reinforcement learning for solving vehicle routing problems with backhauls. Traditional vehicle routing problems with backhaul, VRPB, is a challenging variant of the classic vehicle routing problems, involving two customer nodes. First, delivery nodes. Vehicle deliver goods to the customer. Second, the pickup node, as known as the backhaul nodes. After delivery, vehicle have to pick up the goods from the customers, return it to the depot. However, this type of VRPB has its limitations. First and foremost, the delivery have to occur each and every time before the pickup to avoid any potential delay. This causes a lower utilization of the vehicle capacity and longer detour that can result in resource wastage. As we know, sometimes we can just pick up before the delivery. Thus, with this issue, it leads to the improved VRPB variants that allow more flexible routines, where delivery and pickup can occur alternatively, as long as the vehicle capacity constraints are satisfied. This also results in a more complex problem to solve, as known as the NP-hard non-deterministic polynomial time-hard questions. With this, there are a lot of related work that has been applied. First, exact solutions. Method like set covering formulas and integer linear programming has been applied, but the field to scale with problems as the problem size increases. Besides, meta-heuristic approaches like genetic algorithms and table search has been applied. However, this kind of method depends heavily on the domain experts, limiting the effectiveness in the new problems. Thirdly, neural heuristic methods, which is as known as the deep reinforcement learning, that can apply to automatically learn efficient heuristic from the data, providing more general solutions. With this, author tried to implement neural heuristic to solve the VRPB-based problems on the deep reinforcement learning, which is non-trivial since it's more challenging yet practical.
Thank you, Chiro. My name is Zhao Yun, and now I will introduce the challenge in this paper. The first challenge lies in the intrinsic dual-task nature of VRPP. In a vehicle routing problem with backhauls, we need to handle delivery task, which is called line haul, and also pickup task, which is called backhaul. In a traditional VRPP, the route must serve all line haul customers before visiting any backhaul customers. These three service orders impose strong constraints on route feasibility, reducing the flexibility of path construction and increasing solution complexity. Even in the improved VRPP where the sequence constraint is stiff, the solution space becomes exponentially larger and more difficult to explore efficiently. The second challenge is the complexity of the state space. At every decision step, the state includes the vehicle's current location, its remaining capacity, the list of visit and unvisit customers, and each customer's demand type, which is line haul or backhaul. The state is high-dimensional and constantly changing. Traditional reinforcement learning methods can't handle this complexity well. So the model must use powerful neural network capable of capturing this rich and dynamic state representation. The third challenge is modeling the interaction between different customer types. Customers are not just nodes, they are of different types, and these types influence the decision-making process. A specific attention-based model does not account for the heterogeneity between customer types. The author proposed a two-stage attention mechanism. The first stage captures global structural relationships. The second stage focuses on modeling interaction between line haul and backhaul customers, allowing the agents to learn type-specific decision strategy. The fourth challenge is about ensuring route feasibility at all times. While constructing routes, the models must guarantee each customer is visited exactly once, and vehicle's capacity is never exist. In early training, reinforcement learning agents tend to choose invalid actions, like existing capacity or visiting customers, which destabilize learning. To solve this, the model must implement a masking mechanism to block infeasible choice and continuously update the agent's internal state to prevent illegal behavior. Next, I will briefly introduce the method in this paper. To solve the vehicle routing problem with backhauls, the paper introduced a deep reinforcement learning-based neural heuristic. The method models the routing process as a Markov decision process and uses an encoder and decoder architecture to learn the policy. A two-stage attention mechanism in the encoder captures rich node relationships, while the decoder stack the next node with feasibility ensuring by masking. The policy is optimized using the reinforcement learning algorithm for both traditional and relaxed VRPP settings. That's all for my part. Thank you.
So in the VRPP-RL formulation, the construction of the solution path is actually a sequential decision-making process which can be solved by using deep reinforcement learning, and the model leverages multi-track sampling and training, where each of these tracks begins from the depot node with different line hole node as the first visited node, as to respect the constraints of the VRPP, which is to deliver first and then only pickups. So this will eventually enhance the diversity in learning outcomes by simulating tracks in parallel instead of just one. So additionally, one of these tracks could be modeled as the Markov decision process with 5 tuples. First is going to be the state, which includes all the visited node and the current vehicle loads. Actions, next node to visit, which sampled from the learn policy. Transition, which is resulted from the next state after action is performed and update the route. Reward, which is a negative of total path length, which that aim to minimize and encourage for a short and efficient solution. Lastly is going to be the policy, which is the probability of constructing a complete solution path represented by following chain rule. So at each time step, the path construction, the policy output probability of the node to be selected based on the sample node until complete route is produced. So moving on to the encoder, it involves two-stage multi-headed attention layer, which is the self-attention and the heterogeneous attention. So self-attention alone is not enough to generate information among distinct type of node, which has the homogeneous and the heterogeneous nodes. So it is to help to handle the heterogeneity of the VRBB nodes, since line haul and backhaul customers have different roles. So in order to capture better relationships within the homogeneous nodes and across the heterogeneous node. So initially, the encoder converts the coordinate of each node into high-dimensional embedding using linear projections, which are then being processed by the attention layer. So in the first stage, the graph of the VRPP instance is used to capture the global relationship across all nodes, including the depot, line haul, and backhaul nodes, by exploiting the multi-headed self-attention, as there could be connections in between any of these two nodes. So moving on to the second stage, they have designed a heterogeneous attention specifically to further model the relationship between the line haul nodes and the backhaul nodes and strengthen their representation. So this is also a multi-headed attention layer and dual structured. So additionally, a feed-forward layer is applied to further refine the embeddings, skip connection, and 1D instance normalization in order to improve the training and accelerate the convergence. So eventually, it will produce the node embedding used for the selection of next node, as well as the graph embedding, which obtained from the average of these node embedding, which provide global context as the input for the following decoder.
Thank you, Ishu. Now I will talk about the decoder and the policy optimization. After receiving the output from the encoder, the decoder calculates the node selection probability through the decoding process to determine the node to be visited at each step. In this process, the decoder combines the graph embedding from the encoder, the last visited node in the current partial solution, and the vehicle load as a vector. The decoder leverages a multi-head attention layer and a single-head attention layer to facilitate the node selection and route construction. The function of the multi-head attention layer is to aggregate the information of the context node from the output node embedding. Next, the single-head attention layer is used to derive the node selection probability. To promote exploration and improve marginal performance, the following hyperbolic tangent function is used to adjust the node compatibility between negative C and C. Next, the invisible nodes, including visited nodes, the unreachable nodes due to vehicle capacity limitations, and the depot node for remaining visitable customers, are masked by setting the compatibility score to negative infinity. After that, the decoder calculates the final probability vector by using softmax function. Next, I'll talk about the policy optimization. To train the VRPB for policy effectively, multiple tracks are used, with each track starting from a different line haul node. This is the policy equation used to maximize the reward, and a baseline BS is used to stabilize the training and reduce computation overhead using this equation. So if the current policy network is superior to the baseline network, then the parameter of the latter will be replaced with the former one. And after dozens of training steps in each epoch, the trained policy network could produce high-quality solutions. That's all from me. Now I'll pass the presentation to Pei Yu.
Thank you, Yihui. Now I'll talk about the experiment and result. This paper evaluates a neural heuristic on traditional and improved VRPB, focusing on baseline comparison, generalization, and benchmark performance. In the experiment, two datasets are used. one with a randomly generated instance with customer node size of 20 to 150, where nodes are uniformly sampled in a 2D space with balanced demand. Another one with benchmark featuring more complex distribution. In training and testing setup, the policy network is trained for 100 epoch with 10,000 batch per epoch, batch size of 64, and a learning rate of 0.0001. Validation is done after every epoch, and testing use both dataset with sequential execution for fair runtime. This paper compared the proposed model with both conventional method and neural baseline. In training, the proposed model converts slower than POMO, but achieve better final result. In traditional VRPB, Cplex perform well on small instance but struggle beyond 50 nodes. LKH-3 give best result but is slow. The proposed model outperforms all heuristic with POMO next best. POMO is superior to the attention model and with potential for stronger learning strategy. The attention models scale poorly, while GA and FER face stability and efficiency issue. In the improved VRPB, Cplex solve up to 150 nodes due to the fewer constraint. The proposed model ranks second in small size but performs best at 150 nodes, with better scalability and runtime than Cplex and LKH-3. POMO and FER are close behind, and GA and LNS degrade as size increase. The sampling attention model only suits sample case, while the greedy is much worse. Lastly, visualization show the proposed model generate more efficiency routes than POMO, which providing superior generalization and robustness. That's all for me, and I will pass to Jason now.
Alright, well, thank you, Pei. Good morning, everyone. My name is Jason. Now, I would like to continue with the evaluation of generalization study, where the author tests how well the trained model perform on new unseen instances. First of all, in the cross-site generalization, the model trained on 150 node problem was tested on the larger one with 400 and 300 nodes. In the cost distribution generalization, the same trained model was applied to instances where the node coordinate follow the Gaussian and beta distribution. From the result, we can find that it outperforms other neural baselines like POMO and FER, proving it can generalize across both problem size and data distribution. Moving on, the author evaluated their model on real-world benchmark dataset, which was never seen during training. For traditional VRPB, they have tested on 66 public benchmark instances with various customer distribution and vehicle requirement. Their model have achieved a near optimal result, which is the second place only to the exact solver BCPF2, but with much faster computation. For the improved VRPB, their model was compared to two strong heuristics, which are the RTS and the host. While those heuristics slightly outperform in solution quality, while the proposed model offered a very competitive result in a fraction of the time. This evaluation had demonstrated the strong real-world applicability and generalization of the model. In this part, the author studied how the sampling size during inference affect the performance. They have tested on 4 sampling size. As expected, the larger sample size lead to better solution quality, since more candidates rows were evaluated. However, the key finding is that the model consistently outperforms AM and POMO at every sampling level, even with smaller samples. While this shows the proposed approach is not only powerful, but also more efficient by delivering the high-quality solution without needing excessive computation. Last but not least, the author also analyzed the computational complexity of the model, where they've tested runtime across different problem sizes, including up to 500 customers. The results show that the model's runtime increased categorically with problem size, which are mainly due to the attention mechanism in the encoder. It's worth noting that the custom two-stage attention encoder only add a little extra cost by making the method more scalable and efficient. This balance between the performance and speed is very crucial, especially for the real-world deployment. In the conclusion, the author proposed a deep reinforcement learning-based neural heuristic for solving both traditional and improved VRPB. The model integrates a two-stage attention encoder and flexibility over masking scheme in the decoder by delivering solutions that are not only high in quality, but also computationally efficient and generalizable. In the future, they plan to scale the method in order to handle the larger instances and incorporate heterogeneous vehicle types and minimize the number of vehicles needed. Moreover, they also wish to explore the non-Euclidean routing space and apply more advanced deep reinforcement learning exploration techniques to further improve the model performance. All in all, their work had definitely pushed the boundary of learning-based method in the complex logistic optimization. That's all from our presentation. Thank you very much.